Okay, so um, there is a writing assignment from section 4.7 on applied optimization. Um, Doing the cut out the corners, make the cardboard box. And then there is another writing assignment that I posted yesterday that is based on a graph. So you're provided with the graph of the derivative, and you're asked to determine where is the original function increasing, where is the original function decreasing, and where are the maxima or minima located. So the graph is enough to determine that. We normally didn't do this off of the graph. We normally did it off a number line and notating where the derivative was positive or negative. So you can translate the graph into that information and then answer the questions. But the writing assignments I assign y'all are because they're somewhat similar to test questions. Now, when it comes to word problems, um, I'm more likely to put a slightly harder word problem on a writing assignment than what I would put on the test because you have more time on a writing assignment than you would on the test. So it's not going to be the cardboard box on the test. So the cardboard box one is due today. The graph one is due on Thursday. I accidentally put Friday. I shifted it back to Thursday. And then the grader is going to catch up on grading this week into this weekend. So you'll get some feedback on these writing assignments. Maybe not the last one here, but the other ones for sure by this weekend. He had a upper level math test to study for, so he got a little behind. All right. So let me flip it back to OneNote because we're going to learn about L'Hopital's rule today. So L'Hopital's rule is like the favorite because it takes what used to be really disgusting limit questions and makes them much easier to work with. So when we were first learning about limits and we had to do the limit of a quotient like this, did we need to use a complicated quotient rule like we do with derivatives? And the answer is no. The limit breaks across addition. So I could just do the limit of the top, do the limit of the bottom. But then we have this follow-up question. What happens if they're both zero? So if we get 0/0, it's a moment of panic. What do I do? So usually this indicated do some weird algebra. There's something on the top and the bottom that can cancel out. So indeterminate forms are limits whose values can't be determined immediately without further exploration. So we say 0/0 to represent an indeterminate form where the limit of the numerator and the denominator are both zero. Different limits of this type will have different values. So it's not that 0/0 always equals a particular thing. It just means I don't know what that equals and I have to do something else to figure that out. So like this one here, the limit as x approaches 2 of x squared minus 4 over x minus 2. I do the initial substitution. and I get 0 over 0. So this means rewind back to the drawing board, do something else first. So the x squared minus 4 on top is a nice little quadratic that factors nicely. So x squared minus 4 is the same as x minus 2 times x plus 2. So we got 0 over 0 before because the top and the bottom both had x minus 2 in them. But if I cancel that out, then the only thing left inside the function is x plus 2. So our original fraction function is the same as x plus 2, except when x equals 2, there's a hole in the graph. But the limit here will tell us where that hole is. We know it's at x equals 2, but what's the y value of the hole? So if I plug in 2 here, I'll get that y value. So we had a 0 over 0 form. We did some algebra work, and we ended up with 4.
Yeah.
Now, another weird indeterminate form we had was sine x over x as x approaches 0. So directly substituting in 0 gives us 0 over 0. But proving this particular limit is a little more annoying. But if we look at the graph, we can see that as the x values get closer and closer to 0, the value of the graph actually ends up approaching 1. We can prove this with squeeze theorem or whatnot, but we just learned it as a rule. And that x can be anything. So it can be sine u over u approaches 1. As long as the u's match, that limit always approaches 1. But it turns out that we can be a little lazy. So if I'm looking at the limit of a quotient and my function on the top and my function on the bottom are both differentiable and they contain the a value that we're looking at, except possibly at a, if I get a 0 over 0 form, then the limit of the functions being divided is the same as the limit of the derivative of the functions being divided. Now, this is not do the quotient rule. This is do the derivative of the top, do the derivative of the bottom, and then take the limit of that result. So whenever we get 0 over 0, we can use L'Hopital's rule to simplify things, and the limit will be equivalent, like equal. So whatever value we get from L'Hopital's rule is the same value we would get from other methods. So looking at the same function we just did, we know this gives 0 over 0. So now we're going to use L'Hopital's rule. So I keep my limit the same. And now I'm going to do the derivative of the top on its own. So the derivative of x squared minus 4. Derivative of x squared is 2x. Derivative of 4, a constant, is 0. So I have just 2x on top. And then on the bottom, the derivative of x minus 2. Derivative of x is 1. And derivative of a constant is 0. So now that I've applied L'Hopital's rule, now I'm going to plug the number back in and see if I get an indeterminate form again, or see if I get a number. If I get a number, that's my answer. And we plug it in, we get 4 minus 0 is 4, divided by 1 is 4. So same numeric answer we got before. In order to use L'Hopital's rule, though, you first need to show that you get an indeterminate form. So you don't want to apply L'Hopital's rule all over the place. It's real tempting to do that when you're looking at crazy limits, but you have to make sure you have an indeterminate form before you apply it. So for our weird limit that we learned as a rule, we get our indeterminate form, so we can use L'Hopital. So the derivative of sine on top is cosine. And then the derivative of x on the bottom is 1. So now we substitute in 0, so we get the cosine of 0 over 1. But the cosine of 0 is 1. So there's the same 1 that we learned this is equal to. This is just a different way of arriving at that 1. All right. So now we got a little weird one. So we have the limit as x approaches 7 of this mess. The natural log of 1 is asking e to what power equals 1, and that is e to the 0 power. So this disgusting limit does indeed give us 0 over 0. So now we're going to use L'Hopital's rule. So we'll keep our limit. Now I do the derivative of the top. So that'll be negative 11 times the derivative of the natural log of something. What do we do for natural log derivatives? Yep, 1 over whatever's inside the natural log. So the inside of the natural log here is x minus 6. And then chain rule says we take the derivative of the inside. The derivative of x minus 6 is 1 minus 0. So that's our full long drawn out derivative of the top. Derivative of the bottom works out real nicely though. That'll just be 1 minus 0. Just a 1. So now that we've applied L'Hopital's rule, now we plug in the number and see what we get. So some of these problems in your homework, you'll actually be able to use L'Hopital more than once. Most of them, though, you only need to use it once. So this 1 over 7 minus 6 is 1 over 1, so it's just 1. So we just end up with that negative 11 from the front. So questions so far on how we're using L'Hopital's rule? All right, here's an even more disgusting limit. So we get e to the 0 minus 1 over 0 squared, but e to the 0 is 1, so 1 minus 1 is 0 over 0. So derivative of the top on its own, the derivative of e to the x plus 2 is e to the x plus 2, lazy derivative, times the derivative of x plus 2, which would be 1 plus 0. All right, then the derivative of x plus 3, derivative of x is 1, plus derivative of 3 is 0. Now on the bottom, as it's set up, we're going to have to use the chain rule. So I've got things squared. So derivative of u squared is 2 times u. So I have 2 times x plus 2 times derivative of the inside is 1 plus 0. And now we're going to plug in negative 2 again, see what we get. So I have e to the negative 2 plus 2. So e to the 0 will be 1. Then there's a times 1, still minus 1. And then on the bottom, 2 times negative 2 plus 2. So e to the 0 is 1 times 1 is 1. So we have 1 minus 1 on top, and on the bottom, 2 times 0. So we use L'Hopital's rule. We plugged the number back in, and we got another 0 over 0. So we can use L'Hopital's rule again. Before I use it again, though, I'm going to clean up this whole crazy derivative, like derivative of the top and bottom I wrote, because it's a little ugly looking as it is. So that's e to the x plus 2 minus 1 all over, I'll just distribute it out. So 2x plus 4. Now we're going to use L'Hopital's rule because we proved the 0 over 0. So again, derivative of e to the x plus 2 is e to the x plus 2. But now it'll be minus 0. And then on the bottom, the derivative of 2x is just 2 plus the derivative of 4 is 0. Now when I substitute in, I should actually get values. So we have e to the negative 2 plus 2 again. So that ends up being e to the 0 is 1 over 2. So a whole lot of work to get 1/2. But looking back at the original problem, we don't really have a way to do this otherwise. So what questions do y'all have on how this one shook out? Now we can also have an indeterminate form happen when we're looking at limits at infinity. So each of these, when I'm looking at the limits as x approaches infinity, I get infinity over infinity from the limits. But each of these approaches a different value as x goes to infinity based on the size of the numerator versus the denominator. So if my numerator is bigger, like my 3x squared plus 4x, all divided by x plus 2, remember we simplified that by ignoring all the smaller powered terms. We focused on the biggest terms, and the limit of what that function does is the same thing as what the overall function does. So the x squared, the biggest power is on top. So this limit goes to infinity. Our middle one, the degrees of the top and the bottom are the same. So this limit actually approaches 3/2. And our other one, the x cubed on the bottom is the biggest term. So that means this one overall approaches 0. So they have completely different values as x approaches infinity. But it turns out for L'Hopital's rule, there's also an infinity over infinity case. And it works the same way as the 0/0 case. Now, we can get infinity over negative infinity, or negative infinity over infinity, or negative infinity over negative infinity. We don't really care whether the infinity is positive or negative. Just as long as we get some sort of infinity over some sort of infinity, then we can apply L'Hopital's rule. So looking back at some of those examples, so I still have to check and show that I get an indeterminate form. So if I plug in infinity, as silly as that sounds, three times infinity is still infinity, plus five is still infinity. Then two infinities plus one is still infinity. So I have an infinity over infinity form. I can use L'Hopital's rule. So derivative of the top, 3x plus 5 is 3 times 1 plus 0 over 2 times 1 plus 0, or just 3 over 2. And now there's nowhere to plug in the infinity, so we just arrive at the answer of 3/2. Same answer I pulled out of the hat earlier. So in the past, we dealt with this problem by multiplying by 1 over x all over 1 over x to kind of convert everything into a limit that we knew went to 0. But with L'Hopital, we can arrive at the same answer much quicker. So then we get this stupid mess. All right, so infinity minus infinity is a weird thing to have because we don't know which infinity is bigger or whether they're the same size. So there's actually like a quandary of, is that still infinity or negative infinity, or could it be 0? Now, looking at the equation, e to the t versus t to the 8th, they're not growing at the same rate. If they were growing at the same rate, it'd be like 8t to the 8th minus t to the 8th, or 17t to the 8th minus t to the 8th. It'd be the same variables with the same power. So the infinity minus infinity here is some sort of infinity. So we are getting a L'Hopital indeterminate form. So I can take the derivative, and the derivative starts looking really ridiculous. But I can apply L'Hopital's rule rather. So derivative of e to the t is e to the t. Derivative of t to the ninth is 9t to the eighth. All right, and then if we plug in our infinities, we're going to get, again, infinity over infinity. So we can now use L'Hopital again. So we'll have e to the t plus 9 times 8 t to the seventh over e to the t minus 8 times 7 t to the sixth. And we're still going to get infinity over infinity. So I can actually keep applying L'Hopital's rule a ridiculous number of times. But the e to the t's are going to keep carrying through every result. But the other part of the derivative, the polynomial part, the powers are going to keep coming down, keep coming down. Eventually, the t will go away and it'll just be a constant. And then eventually, that derivative of the constant will be 0. So this many, many, many iterations later, we will eventually end up with e to the t over e to the t, which now those are the exact same thing. So we get 1. So it turns out when we're looking at ridiculous functions like this that have polynomial terms versus non-polynomial terms, the non-polynomials derivatives usually don't go to 0. They'll fall into some weird pattern, or they'll be like e to the t, where we just keep getting e to the t over and over again. So e to the t versus any polynomial, e to the t will always eventually outgrow a polynomial. It may take a really large input value for e to the t to be bigger, but it will eventually always be bigger than any polynomial. Even t to the 1,000,000th power, it takes some ridiculously high values, but eventually e to the t will be bigger. All right, so we have our most basic indeterminate forms. If I get 0 over 0 or infinity over infinity, straight away I can use L'Hopital's rule on my fraction as is. If I get weird forms, like 0 times infinity or infinity minus infinity, I got to do some algebra manipulation, and then I can get it to look like 0 over 0 or infinity over infinity. If I get weird exponential forms, like 0 to the 0, infinity to the 0, or 1 to the infinity, those I can do a conversion, but I'm going to have to use log properties to do the conversion. So the gold standard for indeterminate forms is 0 over 0 or infinity over infinity. If it's anything else, do some algebra manipulation to try to force it to be 0 over 0 or infinity over infinity. All right, now our e to the x function is interesting So as e to the x grows towards positive infinity, the graph shoots up to infinity. But on the left side, as x gets closer, more and more negative. So as x approaches negative infinity, e to the x approaches 0. So our original setup, it looks like we'd have infinity times infinity, but our limit is actually as x approaches negative infinity. So negative infinity to the fourth power times e to the negative infinity we get infinity times 0. So I don't know which of these has more sway over the way the graph is going to shape. I mean, I can make an educated guess that e to the x isn't going to go anywhere in derivatives. But in order to apply L'Hopital's rule, I have to have 0 over 0 or infinity over infinity. So especially when we're dealing with polynomials or exponential functions, when I move something from the top of the fraction to the bottom of a fraction, what happens? Yep, we use a negative exponent. So I could move x to the fourth to the denominator and make it x to the negative fourth. But then if I start doing derivatives of that, I'd have negative 4 minus 5. Like those derivatives are going to get more and more negative powers. So it's not actually going to resolve my derivative nicely. Like I'll just keep getting indeterminate forms forever. So I'm going to move the e to the x to the bottom. So we have x to the fourth over e to the negative x. So now when I plug in infinity, negative infinity rather, negative infinity to the fourth is infinity. E to the negative of negative infinity, e to the positive infinity. That gives me infinity over infinity. Now I can apply L'Hopital's rule. So the derivative of x to the fourth is 4x to the third. The derivative of e to the negative x is e to the negative x times negative 1. Now we're still getting infinity over infinity. Sorry, it'd be infinity over negative or negative infinity over negative infinity. But still, it's some sort of infinity over some sort of infinity. So I can do L'Hopital again. So now we'll have 4 times 3 is 12x squared over e to the negative x times negative 1 times another negative 1 from the chain rule. So it'll be negative 1 squared. Another infinity over infinity, so another L'Hopital's rule. So now we'll have 24x over e to the negative x and then another chain rule, so times another -1. We'll get negative infinity on top, negative infinity on the bottom. But now, finally, my derivative is just the constant 24 over e e to the negative x times -1 to the 4th power. All right, now when I substitute that negative infinity, the top stays 24. The bottom, e to the negative infinity times -1 to the 4th is +1. So my negative infinity becomes positive infinity. So we get infinity on the bottom. So we have a constant divided by infinity. That goes to 0. So we got some weird algebra manipulation, but we did figure out that this limit approaches 0. Go for it.
So, X is at the bottom. It doesn't really matter the sign. Like, it'll just convert to 0, but it does not have, you would have to do all the steps, right? To figure out what's like negative or positive.
Yes, so we would have to keep careful track of the positives and negatives as we move through, just because that can change if it's positive or negative infinity. So whether it's on the top or the bottom, like still keep track of those extra chain rule derivatives. Because yeah, in other problems, depending on what the e to the x is approaching, those negatives can change the answer. All right, our next one is like a disgusting trig bullshit, but with fractions. So as t approaches 0 from the right, we're looking at the limit of 8 over sine t minus 5 over t. So the 8 over sine t so we have 8 over the sine of 0 minus 5 over 0. Sine of 0 is 0, so 8 over 0 is infinity, minus 5 over 0 is infinity. Now here, it's not as obvious to determine like which infinity is bigger or smaller, how they compare. So what we're going to do is we got to do some algebra manipulation. So whenever we have an infinity minus infinity, It has to be minus. If we had plus infinity is just infinity, we're done. But the minus is what makes it problematic here. Because it, like, looking at it symbolically, it looks like 0, but it depends on which infinity is bigger. So we could get infinity, we could get 0, we could get a constant, we could get negative infinity. All of those are reasonable answers depending on which infinity is bigger. So I need to combine these fractions. So I'm going to get a common denominator, add them together. You know what? I'm just going to write it out because that is horrible looking otherwise. So my denominators are sine t and t. So my first fraction doesn't have a t. And my second fraction doesn't have a sine t. So combining the fractions together, I have 8t minus 5 times sine t all over t sine t. All right, now I'm going to plug in the zeros. So I have 0 minus 5 times the sine of 0 over 0 times the sine of 0. Well, sine of 0 is 0, so I got 0 over 0. So that means I can take the combined fractions and apply L'Hopital's rule to this. So we have to get the fraction in the correct form to produce the infinity over infinity or 0 over 0. Then we can apply L'Hopital's rule. So still the same limit as t approaches 0 from the right, but now it will be 8 minus 5 times the derivative of sine is cosine. And then on the bottom, we get a product rule. So derivative of the first one is 1 times, keep the second one the same, sine t, plus, now we keep t the same, times the derivative of cosine t. All right, now we substitute in 0, so I have 8 minus 5 times the cosine of 0 over sine of 0 plus 0 times cosine of 0. Well, cosine of 0 is 1. So on top, it's just 8 minus 5 times 1 is 3. Sine of 0 is 0. Plus 0 times cosine of 0 is 1 is 0. So we have 3 over 0. So when we get a constant over 0, this approaches infinity or negative infinity. Now, since our numbers are all positive and they said we're approaching 0 from the right, so we're plugging in positive numbers. So we had to do some algebra and manipulation to force the L'Hopital form, the indeterminate 0 over 0. Then we could apply L'Hopital's rule, and then we ended up with infinity as our answer. But we only had to use it once because our sine functions turn into cosine functions. So the values flip from going to 0 to approaching 1. So usually when you have trig functions in the mix, you only have to apply L'Hopital's rule once. It's when you get e to the t that you sometimes end up having to use it multiple times. All right. Here is our last crazy example. Now, so A and B are constants. So we're just going to treat them as numbers. So like 2 and 7. So my X here shows up in 2 different spots. But I'm looking at the limit as X approaches infinity. All right, so a constant over infinity is 0. 1 plus 0 is 1. B times infinity is still infinity. All right. So in order to get an indeterminate form here, I need a way to take that power from where it is as an exponent, and I need to be able to bring it down on the line so I can then do algebra manipulation with it. So what takes exponents and pulls them down to the line? What kind of function? Say it again. Yep. Log's whole purpose in life is to take exponents and bring them down. Now, when we have a choice, especially for calculus, we tend to go with natural log because we know the derivative of natural log and we know the derivative of the inverse of natural log, e to the x. Those are our very nice, simplistic derivatives. So technically, though, I could use any log, but I'm going to deliberately use natural log here. Now, it gets a little weird because I can't just apply natural log out of nowhere because I'm inherently changing the function if I do that. So I can only do this if I balance it by undoing it as well. So I'm actually going to apply the natural log and apply the e exponential function. So it's going to look a little weird. So I'm going to apply natural log to this whole thing, and I'm going to apply, let me make that a different color even. So e to the crazy mess, but e to the natural log of the ugly, e to the natural log undo each other. So I've just nested 2 inverse functions. Now, one of the things we learned about limits is as long as the functions we're looking at are continuous everywhere and differentiable on where they're defined, then I can move the limit inside and outside those functions. So my limit as x goes to infinity, I can actually move that outside the natural log. So we're still going to have our e to the, but now this is where we're going to write our limit. And now the natural log is inside the function. Now it's real easy to forget about the e to the at the front of the limit because we're basically going to ignore it for a whole bunch of steps. But at the very, very end, that's going to come back and our answer is going to be e to the whatever our result of the limit is. So when I have a problem like this where I had to do a weird front step, I will sometimes write like a star in front of the function just to remind myself, hey, there's a thing I got to come back and do. This one did something a little weird. So that way I know, like if I type in an answer and Webwork is like, I hate your answer, I look back and I'm like, oh, there's the star thing. I forgot to do the weird extra step. Now our natural log is going to pull down the power. So I'm going to have bx times the natural log of 1 plus a over x. Now, if I plug in infinity, now I end up with b times infinity is infinity times the natural log of 1 plus a over infinity. So a over infinity is 0. 1 plus 0 is 1. The natural log of 1 is 0. So I end up with infinity times 0. This is a very normal thing to happen when you first apply the natural log or get 0 times infinity. Like very often happens. So now we're going to do a little weird algebra manipulation. This b to the x in front, that x, I'm going to move it to the bottom of the fraction. But I move it to the bottom of the fraction either by using a negative exponent, or another way to think about it is to multiply the top and the bottom by 1 over x. Now the bottom, there is no bottom right now. So I'm just kind of sketching it in. So the bx with the 1 over x, those guys will cancel. And on the bottom, I have 1 over x. So the b is going to stay on top. I could multiply by 1 over bx if I wanted. Like it actually doesn't really matter where the b goes. All right, so I still have my e to the out front. I still have my limit. So now I have b times the natural log of 1 plus a over x over 1 over x. Now when I plug in an infinity, the top natural log of 1 plus constant over infinity, 0, natural log of 1 is 0. And on the bottom, 1 over infinity goes to 0. So we have our 0 over 0 form. Now on the bottom, the 1 over x, I don't normally take the derivative of little fractions like that. So I'm going to rewrite that as x to the negative 1 for the purposes of applying L'Hopital's rule. All right, but this is where I can finally apply L'Hopital's rule. I finally got it into an indeterminate form, 0 over 0. So on top, the b is a constant. So it's just going to carry through. The derivative of natural log of something is 1 over the something. Times the derivative of something. So the derivative of 1 is 0 plus a over x is the same as ax to the negative 1. So we'll get times a negative 1x to the negative 2. All over negative 1x to the negative 2. All right, so we applied L'Hopital's rule. Things got a little crazy looking. So let's actually look in here and see if we can't clean this up a little. So here I've got the 0 plus a times negative 1x to the negative 2. So the 0 plus like may as well not be there. So this is times a times negative 1x to the negative 2. So that negative 1x to the negative 2, that's going to end up canceling on the top and the bottom. But before I do that, I'm going to rewrite it so it's a little more obvious that the cancellation is happening, because right now it looks pretty messy. And I want to be sure that it's clear that they cancel. So I have b times the 1 over 1 plus a over x. I'm rewriting it because I'm about to like do some substitution. Times a times negative 1x to the negative 2 all over negative 1x to the negative 2. All right, so I can see those pieces cancel out. So I'm left with a times b over this 1 plus a over x. Now I can plug my infinity in. So we'll have b times 1 over 1 plus a over infinity times a. So the a over infinity goes to 0. 1 plus 0 is 1. So I have b times 1 times a. So I get ab is the result for my limit. But remember, we had this e to the out front. So a times b was the result of our limit, but the answer to the question is e to the ab. One sec, I'm going to see if I can't move all of this. All right. A little bit of cleanup. All right, so this is absolutely like the craziest a limit can get. With some extra numbers thrown in there just to be weird. They're constants, but they're numbers. I don't know because I haven't written the test yet. So there is, in the current version of the test, yes, there is something like this. Not with the A and the B, but I haven't decided if I'm going to leave it or if I'm going to trade it out for something a little less ugly. But L'Hopital will definitely be on the test. So you're definitely going to have a 0 over 0 or infinity over infinity. And I should put at least one weird form that you've got to do some algebra manipulation on. But I've got to like weigh how much algebra manipulation versus the other questions on the test. Because you're going to have a related rates question. You're going to have an optimization question. It's very similar in format to last semester's exam 3. So the practice problems on web work are still good practice. I just have to make some decisions about what I'm actually going to put, how difficult I'm going to make some of those questions. Yeah, probably not one that ugly. So maybe more like this one. All right.